welcome back. Let's get stuck into the steps to conduct an exploratory factor analysis. Did you look outside, see a tree, see a bird? I don't know. That's a weird way to start transition back into a lecture, but uh, I'll keep it in. Hopefully, you did look outside. You enjoyed nature around you. It is good to do. Statistics is about. It takes a lot of internal thought. Take your thoughts external. Maybe you'll see statistics is all around us. I don't know. We'll see how we go. So the 8 steps to understand and conduct an exploratory factor analysis talks about we have to understand the assumptions of exploratory factor analysis. So can you do the analysis on your data? Is your data really suitable for this type of analysis? We have to select the method of extraction. So are your factors likely to be related? We have to determine the number of factors. So what is your data telling you about this? Select the items that fit onto each factor. Name and define each factor. Do those factor namings make sense? Examine the correlations amongst factors, like to what extent are they related to one another. Analyze the internal reliability. Do the items or variables in each factor contribute to a reliable subscale? And then compute composite scores. Don't worry if all of that isn't really fitting. These are the examples that we're going to go through in terms of understanding the steps. Except before we go into that, oh no, I'm going to give you the simulated example. Okay, so I want you to imagine a world where I've collected data on 350 participants, all of you, right? And I've asked you the question, you've done a questionnaire on your brain health awareness, right? And let's say I've asked you 12 questions, so 12 Likert style items scored on 1 to 7. So strongly disagree, strongly disagree, somewhat disagree, neutral, somewhat agree, strongly agree, and strongly agree. So those are, so you have 3 on either side and neutral in the middle if it's 1 to 7. And say I want to ask you questions about your cognitive problems. So I may ask, do you worry about experiencing cognitive issues when you get older? Your cardiometabolic risk awareness for your brain health. So I may ask you statements to what degree do you agree or disagree with the point of high blood pressure can increase my risk of dementia, or heart health and brain health are interrelated. So you'll be, for each of these, I'll design the question. Imagine I designed the questions much better than how I'm articulating them now. But that you're saying, yes, I strongly agree that heart health and brain health are related. And then I may ask you questions on risk reduction, so that I engage in physical activity to help promote my brain health and protect my brain health, or I maintain healthy habits for my brain. You may strongly agree, strongly disagree, or whatnot, somewhere in the middle. And so these are sort of the items that I'm asking you about your brain health. And then I collect all the data, and then I'm going to use exploratory factor analysis to see whether these items cluster onto underlying factors. Now, an important thing is, before we start all of this, is we have to do what we've learned in the basics of this course, which is do our descriptives and get a sense of are the assumptions met for us to be able to analyze this data. And I think this is a key lesson and takeaway in this course. When it comes to any sort of data, any sort of analysis, we have to understand the data and the measure that's there and get a sense of how it's distributed and whether it meets the assumptions for the statistics. And fundamentally, the principle I want you to keep in your mind is whenever you're running any statistical test, it's GIGO is the important thing to remember. Garbage in, garbage out. If your data if you haven't spent time looking at your data, cleaning it, checking for outliers, seeing if there's anything odd going on, then you could run your model. And the dangerous thing is running your model without the descriptives or without checking your data, and then trying to interpret something that may not be interpretable. And this has real implications in the research field. That's why I guess I'm so passionately trying to convey the importance of it, because I see all the time when people come to me with their analyses and they're saying, this doesn't make sense. And many of the questions I ask are about the variables. How are they distributed? How does it look like? And when they start probing and seeing, you realize that many of them can be addressed by some anomaly in a variable. Maybe there's some outliers, maybe it's heavily skewed, maybe they didn't check the assumptions that we're about to check now. So these are really, really important. It's a really important first step. So before we get into analyzing our data that I've fictitiously created and collected from you, let's check the assumptions. So what are the assumptions we have to consider? We have to consider the theory, what makes sense there, the sample size, level of measurement, normality, linearity, outliers, factorability. So we'll cover all of this right now with assumptions. So what do I mean by theory? Well, your exploratory factor analysis should be driven by theory. You want to avoid this fishing expedition in exploratory factor analysis and elsewhere. It can be, particularly in the day and age of secondary data availability, where much of the data is collected, which is a great initiative because many times in research, if you rewind the clock, people would analyze really interesting questions, but it would take, if once you had a question that you wanted to analyze, you have to design a study, you have to go and collect the data, get ethics approval, collect the data, and then once that experiment is done, then you're analyzing that data. And that's still a design that's used today. It's still in effect, but less so, because people recognize that if I'm doing this study and others are interested in the same question, if we just pooled our resources, we would get a larger sample size, and particularly in frequency statistics. And we'll cover this when we talk about power and ability to detect effects. Sample size matters when we're trying to understand or determine whether an effect is there. And so what's important is if you're collecting data yourself and you don't have a sufficient sample size, based on your power analysis, then you may have spent 6 to 8 months investing a lot of time into a question and you're not able to address it properly because you may say, well, we found these results and maybe we didn't find an effect because there's no effect, or maybe we didn't have enough of the sample. And so it's hard to take away, and all the effort and time and investment and resources sort of divvied up that way. I say all of this to emphasize the importance and utility of large secondary data sets, and then tying that back into the thread of the challenge is there are some researchers who use these secondary data sets and run analyses and see what's significant and then publish that and retrospectively fit theory to that. Oftentimes, when this is done, it doesn't hold up because you can't sort of invent theory. You can try your best to weave stories, but fundamentally, what I've found in my research career and when I speak with senior academics and their research careers who are well respected in their research areas, I think what you find is the common thread is that people who trust the scientific process and they ask the question based on the literature, they conduct the scientific method, they update their beliefs based on what they've found and what others have found, and then move forward there. They're not too tied to ideology or hypotheses. A hypothesis is your investigation of what you think would happen based on prior literature, and then you update this based on what you find, and this process typically leads you to what we would perceive as truth or some version of more and more interesting questions that unravel itself. The challenge when you do something like fishing is that you go down the rabbit hole of looking at effects, retrospectively fitting something, and then trying to progress research from there, but it won't often give you the result because sometimes these results may be due to having too much of a sample size, and you detect these effects and you put too much weight or emphasis on them. And so with EFA, which particularly is a data hungry activity, what I mean by that is it uses a lot of, the more data it has, the better it is to conduct. It can be, and the process of EFA, it can be something where people may retrospectively be fitting ideas into by exploring the data itself. And so you want to avoid that fishing expedition and make sure that actually what I'm doing is driven by the theory that's available in this research area. So you, for example, you might be asking, how many distinct dimensions or factors of X are there, and what are they, and which items best represent these factors? So already, even though it's exploratory in nature, you're trying to understand more about what the factors are, what are they, and which items best represent those factors. So let's talk about sample size. So that was ensuring that it's theory driven, and this is for factor analysis, but pretty much every question that you have should be informed by theory, and that theory can be previous literature, or if you're really doing something that hasn't been seen before, it may be through clinical observation. You may see something in the clinic or something in the world, and you say, well, that's something that I'm observing, now I want to test it. And that in itself can be something to form the foundation of that line of inquiry. Let's talk about sample size. So factor analysis, I mentioned this in relation to theory, but it requires a bigger data set than many other analyses. So how many cases of data do you need? This depends on the number of variables you have. I should say that you're going to hear a lot of rules of thumb, and you have already in correlation section of this course. But these rules of thumbs, and I think I emphasized it there as well, they're just guidelines. It's always about interpreting your data in the context of these guidelines, having them as a useful measure to get started, but also interpreting what your results mean in the context of those guidelines. So here, the guideline proposed here is at a minimum more than 5 cases per variable, so a 1 to 5 variable ratio, like variables to cases ratio. So if you have, for example, 12 items or 12 variables on a questionnaire, you want at least 61 participants there filling out that questionnaire. An ideal is more than 20 cases per variable, so 1 to 20 ratio. The total number of cases should be at least 200, ideally more, and these are guidelines by Comrie and Lee in 2013. So say 50 cases is very poor, 100 is poor, 200 is fair, 300 is good, 500 is very good, 1,000 plus is excellent. Again, these are just guidelines. Take it with a grain of salt, but important to consider the core message is that factor analysis is one that requires a lot of data, and the more data, the better. If you have less data, just be sure to be tempering conclusions or be cautious of interpretations in the context of the data that you have, particularly if it's at least below these thresholds. That's something to keep in mind. So how many cases do people usually use is a good question. And so Fabregat looked into this and found that in two of the top journals, there was a range of sample sizes used. So Journal of Personality and Social Psychology and Journal of Applied Psychology. What they found was how many used 100 or less, about 20% in this journal and 14% in this journal. And keeping in mind that 100 or less, 100 is typically poor in this context, but also it depends on the variable to ratio that's there. But when you say more than 400, there was about 30%, right? So, but less than, cumulatively, we're talking 30, 45% of people here, and similarly 37, 8% of people here are using less than 200 participants, right? So quite a large number of people are progressing with exploratory factor analysis without maybe the sample size that's needed. Again, it's important to consider what this means in the context of the number of variables that are there and the sample size to variable ratio, and also how they talked about their conclusions, right? And did they acknowledge sample size in this? So there's many ways about it, but this is just to highlight that there are a range of sample sizes that are used in EFA. EFA being exploratory factor analysis. Hopefully you're familiar enough with that I can say it, but I'll try to say it in full where possible. Level of measurement, you're well accustomed to this by now. So in order to be included in exploratory factor analysis, your variable must be suitable for Pearson product moment correlational analysis. So what does this mean? Your measures need to be interval or ratio level of measurement. So all your items need to be at the interval or ratio level of measurement when you're analyzing it. So that is important to consider, and of useful consideration when you think back to what we spoke about when we were talking about levels of measurement and whether Likert scales fit into ordinal or interval, right? So if it's ordinal, then technically exploratory factor analysis is not appropriate for those sort of measures. But if it's interval or ratio, it's okay to do so. And again, that barrier between ordinal and interval, if you have a scale, Likert scale of say 3, there's a stronger argument that it's ordinal than interval. Whereas if it's 5 or above or 7 and above, it's more, you can make a stronger argument that it's interval rather than ordinal. And again, for the purpose of this course, we'll be viewing it all as the lens of interval for these Likert scale data. But I wouldn't be doing my job as an academic if I didn't highlight the true nature of the discussion and discourse around Likert scale measures as ordinal or interval. And so you can look that up further as well if you're interested. So normality, so factor analysis can cope with minor violations of normality. It's relatively robust, and what this means is if your data is not normally distributed, it can cope with this. However, it works best if the variables are normally distributed. So, but if it's not fully normally distributed, the analysis is able to cope with these minor violations of normality. So it doesn't mean you can't do it. I talked about outliers. Well, factor analysis is sensitive to outliers, including bivariate outliers. So this is outliers between two variables that result in an outlier, or multivariate outliers. And so you may be asking yourself, well, what is a multivariate outlier and why are they important? Well, I've given an example here of someone who's 18, postgraduate, and has 3 children. This person, if they exist, is more often than not likely to be an outlier, not typical to the normal demographic that you'd see of someone coming through university, because they're very young and they have 3 children and they're in a postgraduate education. However, if you took each of these variables at face value and you looked at them individually, they wouldn't actually stand out as an outlier. If you looked at the age range of students, you'd see the distribution and you'd see that they fit within the distribution there. Whether people are postgraduate or undergraduate, they would fit within there. And how many children people have, there would be a variability there, but they'd fit within there. They wouldn't really stand out as an outlier. However, when you put all 3 together, they become a very clear outlier. So that's where multivariate outliers come into play. And so how do you identify outliers? Well, scatter plots. And scatter plots are useful because it allows you to identify multiple things at once. It allows you to identify whether there's clusters of outliers that are present, and also whether there's your data's meeting linearity, your assumption of linearity, which we'll come to. You can also use something called Mahalanobis distance, which allows you to identify whether outliers are there in your data, and then you can investigate whether they're influential. And so what do you do when you have outliers? Yeah, you either remove them if you think that they don't actually reflect your true population or sample that you're looking at, or recode them if they're influential. But typically you evaluate why they're there. Why are they outliers? Is it an issue that's present in the overall coding of the person? Is it maybe that the data is it plausible? Is it implausible? And then you ask yourself, well, if I was to do the analysis with and without the outliers, does it change? If it doesn't change or it's not influential, I think that's a good sense to just retain it. If not, it can be. If it does change, you can report it changes with the presence of these outliers and show what happens when you remove them. So linearity, I said check the scatter plots because you can use scatter plots to assess linearity of variables as well. So why is this important? Well, factor analysis is based on correlations between variables, and correlations are a measure of the linear association between variables. So it's important to check that variables are linearly related. If they're nonlinear, it violates this assumption of linearity for factor analysis. Factorability, what does this mean? Well, there has to be factors to do a factor analysis. So factorability assesses whether there are sufficient intercorrelations amongst the items to warrant factor analysis. So you have to ensure that when you're looking at the items there, and we'll show you what a correlation matrix is in a moment, but when you're looking at the items that are there, you're ensuring that actually, yeah, it looks like there are clusters here that could form factors. So we can assess it via one or more of like a correlation matrix correlations, so whether those correlations are greater than 0.3. An anti-image matrix diagonals. So this is where you actually, depending on the software you're using, it's typically in the diagonal, and you see the partial correlations, which is the correlation, the relationship between two variables adjusted for these others. You don't need to worry too much about that, but just know that it's an anti-image matrix, and you look at the diagonals, see if it's greater than 0.5, and measures of sampling adequacy. So we have Bartlett's significance and KMO, whether it's greater than 0.5 or 0.6. So we'll go through these in more detail through the example, but this is just emphasizing that these are ways to know whether your data is factorable. So do you have distinct factors? Do items cluster together onto distinct factors? And this allows you to tell that. So here's an example. Great, to get straight to the example. So is the correlation matrix of our data set factorable? As a reminder, our data set had 12 items looking at cardiometabolic awareness, cognitive worry or symptom concern, and self-efficacy of what people are doing for their brain health. So all of these things are looking at this survey that I've created about brain health. And so what I've done is done a correlation matrix. So you can see across the middle there, it's 1 because it's correlating itself with itself, right? Cardio 1. So it's item 1, cardio 2 with cardio 2. And then what we see here are correlations. So what am I looking for in this table? There's a whole bunch of numbers, a whole bunch of correlations. Well, we're trying to see if there are little clusters that are occurring here, right? So if you look at, say, cardio 1, 2, and 3, you can see that there's a cluster that's occurring here of correlations, 0.5s, 0.4s, and they're all sort of clustered together. And then if we, again, shift across to, say, the cognitive variables, right, and we look what's going on here, we can see, actually, yeah, there seems to be this cluster of 0.4s over here with cognitive variables. So they do seem to be correlated. Actually, some of them seem 0.3s over here. So there's some cluster of correlations around here. And then if you're looking at self-efficacy measures, well, these are all pretty low over here in self-efficacy. And then we get a cluster of some 0.5s, 0.4s over here. So looking at this correlational table, we can see clusters of correlations above 0.3, right? Ideally, even more than that, but at least 0.3 that's occurring. So we would say to ourselves, look, looks like there are clusters that are occurring, so our data set is factorable. And if this was just variable 1, 2, 3, and all the way to 12, you would still be able to identify this, so you'd be able to see that clusters. But I know it's difficult initially when you're looking, but try to get like that circle and try to see, okay, where are the numbers greater than 0.3, and are they all next to each other? Oh, okay, so maybe that's a cluster that's occurring there. And are there any other 0.3s? Oh, here's another, maybe that's a cluster occurring there. So try to keep that lens when you're looking at a correlational table, and that helps identify whether it's factorable. So what's the anti-image correlation matrix? Well, the nice thing about R and producing it here in R is that it just gives you the line item for the anti-image matrix diagonals, which is what we see here. And in this fictitious data set I've generated, it's all greater than 0.5. So this is another indicator that our data is factorable. Yeah, so we have a correlation table, all greater than 0.3, which is good. We're having clusters of 0.3s here. So that indicates it's factorable. Anti-image correlation matrix indicating it's factorable because they're all greater than 0.5. And then we have 2 more tests. We have the Bartlett's test of sphericity, whether it's significant. So that's on the bottom here. It's a chi-square test here. And we can see the p-value is something incredibly small. What that means, e to the negative 211 means move the decimal place to the left 211. I don't know why I can't say that. 211 spots. So you want to move to the left that many spots, and then so your p-value is 0.000 all the way down. So you know it's very, very small. So it's significant. So that's a good sign that it's factorable. And then our KMO, which is Kaiser-Meyer-Oakland factor adequacy, that is 0.883. So it's greater than 0.5 or 0.6. So this is the fastest method, but least reliable. And what I mean by that is you want to sort of ensure that you're using multiple levels of evidence, not just, oh, I ran a KMO, it's greater than 0.5, so it's probably factorable. You want to actually tie all the evidence together. Say, look, I looked at the correlation matrix, I could see clusters greater than 0.3. I looked at the anti-image matrix, correlation matrix, I can see it's greater than 0.5. KMO and Bartlett's test, and I can see that it's significant for Bartlett's test, and KMO is greater than 0.6 right here. So all of this put together allows us to say that the data set's likely factorable. And so that's really the key takeaway. If you're just using the statistics alone, it can be quick, but it may not be as reliable. So your correlation matrix is factorable if several correlations are above 0.3. The anti-image correlation matrix diagonals are above 0.5. Bartlett's test is significant and KMO is greater than 0.5 or 0.6. So those are all the things whenever you hear these points, I want you to be thinking, oh, okay, all of that relates to the factorability of our data. What does factorability mean? Again, it means you can get distinct clusters of items together that measure a factor, measure a construct, and that's what you see there. That's factorability. Excellent. So that is everything in terms of factorability. So now we're going to talk about which extraction method do you use after we come back from this short break. So go look out a window again. Maybe it's the same window, and come back. And I hopefully promise that the transition back won't be as disastrous as the last one. So I'll see you soon. Okay, enjoy your break. Come back in a moment.